Okay, so we've seen this problem over the last couple of weeks. The first step here, since we're not told what dilution we're using, instead we're given the amounts, the first step is to find the dilution. And if you recall, in a dilution, we have the amount of the serum, in this case the amount of the blood, or the number of parts of blood, to the parts of the total solution. So in this case, we had the 40 microliters of blood, 120 milliliters. You got to be careful. 120 milliliters is 120,000 microliters. Have to keep those units the same over 40 microliters. So now we reduce that. We have 40 over 120,040. It's going to be a pretty rough reduction there. Both of them do divide by 40. So I'm just going to divide them out by 40. That is a 1 in 3001 dilution. So 1 in 3001 dilution. The 197 is the diluted reading, so that's going to go on top. That's the smaller number, assuming that our true reading is larger than that. It will cross multiply and divide. So 3001 times 197 divided by 1 is 591,197. Now, I realize that's a ridiculous reading, but I wanted you to get used to the numbers, and I wanted to kind of emphasize that, making sure those are the same units in a dilution. Some other things we've done with the dilution. Oops. I got to pause here. My word didn't get searched for it. So one of the other things we saw is, let's say that we have a 48% dilution, or sorry, 48% solution. Is put through a 1 in 6 dilution and then a 1 in 2 dilution. I want to find the final concentration. Well, when we're dealing with a solution concentration and a dilution, the ratio of the concentrations is equal to the dilution ratio. So the 48% is before the dilution, so that's going to be the larger of the two, so that's going to go on bottom. We cross multiply and divide. 1 times 48 divided by 6 is 8. So after the 1 in 6 dilution, we have an 8% solution. Then we do the 1 in 2 dilution. So that 8% is going to be the higher concentration there. Cross multiply and divide. 1 times 8 divided by 2 is 4. So after the second dilution, we're at a 4% concentration. We use that concept there to dilute solutions and get volumes, but we found a simpler way of doing it, and that was our formula: concentration 1 times volume 1 equals concentration 2 times volume 2. And we use that to say, you answer questions like how much saline is needed to dilute 160 milliliters of 28% solution to 21%. So as we're looking at this, our initial concentration is the 28%. We can either make that a 0.28 or we can leave it as 28. Remember, in this formula, as long as we have both concentrations the same, it doesn't matter. So to simplify it, I'm going to leave it as 28. My volume is 160 milliliters. On the other side, I want it to be 21%, and I am looking for that final volume. So do the 28 times 160. 4,480 equals 21 times V2, and we divide by 21. So 213 and 1/3 milliliters is the volume of saline or sterile water required to dilute that solution. Well, then the very last thing we did last week was the different types of figuring in a concentration. So we might be asked, how much sodium hydroxide would be used to create 300 milliliters of 9% weight in volume solution. Weight in volume, remember, means that the top number is a weight in grams and the bottom number is a volume in milliliters, because grams and milliliters go together. And the top, of course, is just the medication or the concentrate, and the bottom is the total solution. (9% means that ratio is 9 out of 100. We have 300 milliliters of our total solution, and we cross multiply and divide. 9 times 300 is 2,700, divided by 100 is 27, and that unit will be in grams. So it takes 27 grams of sodium hydroxide to create that solution. Now remember, in a weight in volume solution like this, if you were creating it, you would put the medication in, and then you would have your level, the 300 milliliters, and you would fill with saline until you reach that level. There is really no way to predict what the volume of that saline would be. Same type of thing happens with a volume in volume solution. Let's say how much alcohol is needed to mix 240 milliliters of 21% volume in volume solution. So again, volume in volume, it doesn't matter what units we use as long as both of them are the same. Could be liters, could be milliliters or microliters. 21% is 21 out of 100. And remember, the 21 again represents the medication, and the 100 is the total solution. And of course, the 240 is asking about the total solution, 240 milliliters. So here we will cross multiply and divide. 21 times 240 divided by 100 is, what is that, 50.4 milliliters? Yes, it is. So it takes 50.4 milliliters of alcohol to create that solution. Now again, in a volume solution, these are not additive. I could not take 240 and subtract the 50.4 to figure out how much saline it's going to be. If I subtract that, it would give me the minimum amount of saline, but it might take more. Oh, let's say I'm going to word this one just slightly different. How would you mix 250 grams of a 9% sodium hydroxide? I should do 9% weight in weight sodium hydroxide solution. Now here I didn't just ask how much of the sodium hydroxide, I asked how would you mix it. Because this is weight in weight, we can figure out a little bit more here. 9% is 9 out of 100. The 9 is still the amount of medication. And the 100 is still the total. We're mixing a total of 250 grams. Now, since this is weight and weight, it doesn't matter whether you use grams or milligrams as long as both are the same. But this one gave us grams. 9 times 250 divided by 100 is 22.5 grams. So that is 22.5 grams of the sodium hydroxide. But I said, how would you mix? So that implies I'm looking for the other side of it as well. Since this is weight and weight, these are additive. So I take the 250 grams of the total solution minus the 22.5 grams of sodium hydroxide, and I get 227.5 grams of saline. So when it's weight and weight, I can figure out the amount of saline. Well, to start off today, we're going to switch gears just slightly. We're going to look at loading syringes. And to work on loading a syringe and figuring out how to load a syringe, first thing we need to do is talk about scales. First thing that would happen on these is they would be labeled, usually milliliters. And then there's going to be numbering. So this might be numbered 1, 2, 3, 4, and whatever. So the first thing we need to do is figure out what each marking means. Now I drew these syringes, I sketched these out, I drew them pretty square on the end here. Normally the tip of the syringe is beveled. And because of that bevel, the markings at the very beginning of the syringe are often hard to read. So I normally would not start at the beginning, I would start at 1 or one of the other numbers, and I would go from that number to the next. So that range there is 1 milliliter. I'm going from 1 to 2. So 2 milliliters minus 1 milliliter is 1 milliliter. And then I need to count the number of spaces, the number of divisions between them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 divisions between them. I divide that out. 1 milliliter divided by 10 is 0.1 milliliters. So each division on this syringe is 1/10 of a milliliter. So if I am filling this syringe, or if I'm looking at this syringe and it's filled to here, I would read that by going, okay, of course I covered up my numbers when I used red, didn't I? Here's my first number smaller than that, that's 3. Each division is 0.1, so it's 3.1, 3.2, 0.3, 0.4, 0.5. Now you probably could have found the 3.5 on your own just because there's a middle mark there. 3.6, 3.7. So that syringe is holding 3.7 milliliters of fluid. This next one here, it's labeled like that. So again, I'm going to start at 1 and go to 2. So that is 2 milliliters minus 1 milliliter. Now the only reason I'm doing it like that, I mean, we all know that that's a 1 milliliter range, but in some of the problems we see coming up, that won't be just a 1 milliliter range. So we'll have to work it out. So then we count 1, 2, 3, 4, 5. Now I know that there's 5 divisions between here and here, so I'm just going to go 5, 10, 15, and 20. I'm not going to count each of them out individually. So I have 1 milliliter over 20 divisions. That's 0.05 milliliters per division. So again, if I fill this syringe, like that. Now I could start at the 1 here, and I know that each division is 0.05. So that's 1.05, 1.10. I'm just going to count 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So that's 1.5. 55, 60, 65, 70, 75, 80, 85, 90. So that's 1 and 90 hundredths, or 1.90 milliliters. But often it's easier to start at the higher number and count backwards. Since this is really close to the 2, I could just count back. 2 minus 0.05 is 1.95, minus another 0.05 is 1.90. A lot of times it's easier to think of these as hundredths when they're divided up like that and count by 5s. Now, if each of these is 0.05 or 5 hundredths, so then this would be 2, this would be 95, this would be 90, 1.90. So we might have one labeled like this. So again, I'm going to go from one mark to the next, the one labeled mark to the next. So that's 3 to 6. So 6 milliliters minus 3 milliliters. There are 5 divisions there. So there's 3 milliliters split up over 5 divisions. Each division is 0.6 milliliters. So this syringe, it's filled to that point right there. So again, we've got 21 here. Now this is going to get a little bit trickier. This is 21.6. Another 0.6 would be 22.2 and 22.8.
Hey Todd?
Yes.
Is there any way, because this is a lot of information, that you could make a worksheet or something of this that you've done so that we have a copy of this?
For the syringes?
Yeah.
I can save this worksheet as I'm drawing it out and send it to you guys later. I'll post it on Blackboard for you.
Awesome. Okay, thank you.
You bet. Now this syringe here, sometimes you'll see them labeled cc's rather than milliliters. What's the difference between a milliliter and a cc? They're exactly the same. 1 cc actually stands for 1 cubic centimeter, which is 1 milliliter. So let's say we have something like this. 5, 10, 15, 20 is how it's labeled. So again, we're going to go from 5 to 10. So 10 milliliters minus 5 milliliters. That's a 5 milliliter range. And if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 divisions in between them. So 5 milliliters divided by 10 is 0.5 milliliters per division. So again, if we fill the syringe like that, well, here we got start at the 15, and each division is 0.5, so we're going to count up by 0.5s. So 15.5, 16, 16.5, and 17. So that is at 17 milliliters is where that syringe is filled. Now, an important thing with these syringes is to figure out which syringe is appropriate to use for a given dosage. So let's say that the required dosage, in fact, I'll write it down here so I can see both syringes in the picture. The required dosage is 4.8 milliliters. And this one is labeled one, 2, 3, 4, 5, 6, 7, 8, 9. And this one's labeled like that. Well, this one up here, if we go through, that's 1 milliliter over 5 divisions. So that is 0.2 milliliters per division. So 4.8 would be found, here's 4, 0.2, 4.4, 4.6, 4.8 would be right there. On this syringe here, that's 1 milliliter, but that's split up over 10 divisions, so it's 0.1 division, 0.1 milliliter per division, I should say. So here's 4. This would be 4.1, 2, 3, 4, 5, 4.6, 4.7. This syringe won't hold the 4.8 milliliters. So we're not going to use that syringe. This would be the one we would have to use if those were our two choices. We don't want to have to stick the patient twice to give them their dose. But let's say we had an ordered dosage of 1.9 milliliters. And let's say we got this one. Come on. Labeled 1 and 2 like that. And this one here labeled 1, 2, 3, 4 like that. Well, for this one here, that's 1 milliliter, or 2 minus 1. And if we count them up, there are 20 divisions. So 1 divided by 20 is 0.05 milliliters per division. So to find 1.9, I would actually count backwards from the 2. So 5/100ths of a milliliter per division. So I'd count that as 200, 195, 190. So there's my 1.9 milliliters right there. On this other syringe, this is 1 milliliter range, and 2 minus 1. There are 10 divisions in between there. So that is 0.1 milliliter per division. So if this is 2 counting back, that's 1.9 right there. Or we could do 1, 1.1, 1.2, 1.3, 1.4, 1.5, 0.6, 0.7, 0.8, 0.9. So 1.9 is going to be right there. Either one of these syringes will hold that dosage. Which syringe do we want to use, the top or the bottom? Careful. The top syringe is actually more precise. And the reason for that is the numbering on all these syringes are drawn the same size. But a syringe like this where the numbers are further apart, that's generally going to be a narrower syringe. One like this down here where the numbers are closer together so it gets a higher volume, typically that's going to be a wider syringe, a fatter syringe. When you're filling these syringes, there's always going to be an error. You are never going to get that plunger exactly on that line. It's always going to be slightly off. On a thinner syringe, the amount that you're off, if you're the same distance away from the line, it's less volume because it's a narrower syringe. On the wider syringe, being off from that line a little bit is going to be more of a volume of error. So when you are dealing with syringes, the full syringe is always preferable. The fuller the syringe, the more precise it is. So if you have your choice between a syringe like this one and filling it just under half full, or one like the one on top here and filling it almost full, the top one is the one you want to use. That's going to have less error in it. Now, up here, you might be wondering, well, this would have been less error to use the bottom one, but the bottom one didn't hold the full dosage, and as we said, we don't want to stick the patient twice if we don't have to. Okay, any questions on filling syringes? Okay, what I will do is I will actually put this worksheet out there that I've done here, and then I will put a blank worksheet on Blackboard so you can put your own scales in there and mess around with them if you want to.
Thank you.
You bet. Okay, so our next step then is we want to talk about looking at drug orders. We're not going to spend a lot of time talking about abbreviations, but in your textbook, on page 150, there are a lot of abbreviations listed there that would appear on the drug's label and on the doctor's orders. Some of the ones like IM or IV are describing how the drug is administered intramuscularly or intravenously. Those mathematically don't mean a whole lot to us, but of course, in your clinicals, those would mean a lot. The ones that mean more for us are like Q6H, which means every 6 hours. Q4H, every 4 hours. And then, of course, the abbreviations that tell us, twice a day or daily or things like that. Again, there's PO, which means orally. Don't mean so much for us on the math side, but are things that you will need to know. So I'm not going to go over them so much in class, but like I said, page 150 in your book, I would mark it or something so that you can refer back to it quickly to find those abbreviations. Okay, so now I've reached that point where it's time for us to actually start in on the dosage calculations. Now, when we're doing the dosage calculations, there are actually 3 methods of calculating the dosages. And I'm going to go through them in order from my least favorite to my most favorite. The one that the textbook tends to really stress is the dosage calculation formula. The problem with the formula is it's a little bit cloudy to understand. The second method is a proportion. Kind of like we did with some, we could do some of our rates, speeds and stuff like that with a proportion. We can do our dosage calculations with proportions as well. Except if it's multiple step, you've got to set up a separate proportion and do it over and over again. And then we have, the reason we've stressed this one so much, dimensional analysis. Dimensional analysis is just a really big word for using measurement conversions. And the key to those measurement conversions that make them work is a unity fraction. So before we get to our first break here, let's talk about the dosage calculation formula. For those of you that are in the ADN program, or they're going into the ADN program, I haven't looked at your dosage calculation book in the last couple of years, but a few years ago, the one that you had did stress this dosage calculation formula. The problem with the dosage calculation formula, there's two problems with it. One is it only applies to only certain problems. So then you need different formulas for different other types of problems. And the second is, in more complex problems, you'd have to apply it more than once. Well, let's take a look at it in some simple examples. So the dosage calculation formula is, you take the the doctor's orders, divided by H, the on-hand dose, times V, which is the vehicle. That gives you A, the amount to administer. So D is the doctor's order, or the ordered dose. H is what is called the on-hand dose. That is what's in the vial or the bottle. So the on-hand dose comes off of the label. V is the vehicle. That's what carries that on-hand dose from the bottle or vial into the patient. And A is the administered amount. So that's what you actually do give the patient. The easiest way to interpret this formula is with capsules. So let's say your doctor orders 1,300 milligrams of ibuprofen. Q4H every 4 hours. Your bottle or your label says 500 milligram tablets. So in this problem, the doctor's order is easy to pick out. That's the 1,300 milligrams. So that's D. Now, the doctor's orders and the on-hand dose must have the same units. So since we have milligrams for the doctor's orders, the on-hand dose must also be in milligrams. Well, this is 500 milligram tablet, so that means 500 milligrams goes down here. The vehicle, what carries the 500 milligrams to the patient? That 500 milligrams is contained in one tablet. So from that, we will calculate what we administer to the patient. So here, milligrams divide out, cancel out. 1,300 divided by 500 is 2.6. Times one tablet is 2.6 tablets. Now that's mathematically possible, as we'll discuss a little bit later, might not be medically or physically possible. In fact, why not mention it now? If the word scored appears in there, if it said 500 milligram scored tablets, what does scored mean? Does anybody know? It's perfect. It means it's got that little notch in it, so you can very easily break it in half. Most tablets, if they're scored, that implies that they can only be a full tablet or a half tablet. So we would probably have to say that this would be 2.5 tablets that we would administer to that patient. Some of them, I mean, very rarely, but there are some that are scored down to a quarter tablet. So we will look at that possibility too in some of our issues or some of our problems. But usually tablets, you either have to round to the nearest tablet or if it's scored to the nearest half tablet. You might have a doctor's orders that say administer 250 milligrams of medication. I'm not going to put a time frame on here. You're looking at the label, and the label says 25 milligrams and 2 milliliters. So again, what's the doctor's orders in this problem? 250 milligrams. The on-hand dose then would be, it has to have the same units as the doctor's order, so the only thing there is the 25 milligrams. Excuse me. The vehicle is usually a little tricky at first. What carries that 25 milligrams into the patient? 2 milliliters, yes. Usually, the on-hand dose and the vehicle come from the label. So that 25 milligrams is contained in 2 milliliters of that solution, or that fluid. So we use that to figure out how much is administered. So here we got milligrams divide out. 250 divided by 25 is 10. This number should always be unitless after we divide it out. The unit should always disappear. The vehicle, the units of the vehicle will give us the units of what we're going to administer. So 10 times that vehicle of 2 milliliters, we would administer 20 milliliters of that medication to the patient. I'm going to have you guys try one in your notes. Let's say the doctor orders 180 milliliters. The label says 180 milligrams, that should be up here. Doctor orders 180 milligrams. The label says 2 milligrams in 5 milliliters. Calculate for me what the administered dose should be. So what is our doctor's order here?
180.
180. On hand? 5. Vehicle?
2 milliliters.
2 milliliters. So again, we're going to divide out the milligrams. 180 divided by 5 is 36. So then 36 times 2 milliliters, 72 milliliters is going to be administered to the patient in whatever time frame that consists of. Okay. The problem with the dosage calculation formula, as I said, is it's a little confusing, but also it only applies to the specific problems where you have a doctor's orders and a direct relationship on that label between the units that the doctor ordered and what needs to be administered to the patient. You might have a doctor's order for 250,000 units of a medication. And on the label, you might have 100,000 units per gram and 250 milligrams in 4 milliliters. So in a problem like this, if I were to use the dosage calculation formula, I have to start out with the doctor's orders of the 250,000 units. And of course, it has to be 100,000 units on bottom here because you have to have the same labels. Well, that 100,000 units is contained in 1 gram. Now, I could either do this with the 1 gram and then take an extra step before I get to the second process, or since I see this is in milligrams, 1 gram is how many milligrams? 1,000. So I could change that gram to 1,000 milligrams here to save myself at least one step in this calculation. So the units cancel out. 250,000 divided by 100,000 is 2.5 times 1,000 milligrams. Well, 2.5 times 1,000 is 2,500 milligrams. To figure out what I would administer to this patient, however, I still have to go back. I have to get 250 or 2,500 milligrams into my patient. Now we're using the second conversion here, is the on-hand dose would be the 250 milligrams, and the vehicle would be the 4 milliliters. Milligrams cancel out. 2,500 divided by 250 is 10, times that vehicle of 4 milliliters is 40 milliliters that would be administered to the patient. So you can see there's a couple levels there. In fact, I saved us a step by putting that as 1,000 milligrams instead of 1 gram. So there would have been an extra step in between here if I hadn't done that. But you can see this dosage calculation formula is a little bit tedious in that way. Okay, it is time for a break, so let's go ahead and take a break. It's 9:21. Let's come back at 9:31.